Right. Good morning, all. I'd like to just kick off right away and dive straight into our material. So today we are going to start working on section 17.4 on Green's theorem. As you may recall, there's three big theorems in this chapter: Green's theorem, Stokes' theorem, and the divergence theorem. And today we get the first of these. So the preceding section gave a version of the fundamental theorem of calculus that applies to line integrals. In this lesson, and for the remainder of the course, you will see additional extensions of the fundamental theorem of calculus that apply to regions in R2 and in R3. All of these fundamental theorems share a common feature. So if you think about the fundamental theorem of calculus from a couple quarters ago, the basic gist was you took the integral, the definite integral of some function, and to evaluate it, you evaluated the antiderivative at the two endpoints and you found the difference. So evaluate a definite integral by finding the antiderivative and evaluating it at the two endpoints. If you think about the fundamental theorem of line integrals from yesterday, we wanted to evaluate a line integral of a gradient field. You can think about a gradient, the potential function is the antiderivative of the gradient field. And so to evaluate that line integral, we evaluated the potential function at the two endpoints and found the difference. Same concept. So the subject of this section is Green's theorem, which is another step in this progression. It relates the double integral of derivatives of a function over a region in R2 to function values on the boundary of that region. So let's dive straight in. So we're going to look at a couple of different forms of Green's theorem, and today specifically we're going to focus in on the circulation form of Green's theorem. As you may recall, circulation is sort of like the work to go around a closed loop. So circulation's the work. It's like the work around a closed loop. So recall that the circulation of f dot dr equal to the line integral around the closed path of f dot t ds measures the net component of f in the direction tangential to c. So remember tangential, and there you've got the t. This is going to be important when we get to the next version of Green's theorem. So a non-zero circulation on a closed curve says that the vector field must have some property inside the curve that produces the circulation. And so you can think of this property as a net rotation. So let's check out our first manipulate. So here you have the unit circle, and so we can follow along the unit circle, and we're traveling counterclockwise. And notice the red vectors would represent the vector field f equals negative y comma x along that unit circle. And so notice as we go along that our wheel is spinning all the way along the curve, and it's always spinning the same direction. And so we could ask, what's the total circulation? How much is it spinning altogether when we go around the path? So that's kind of a, and so you have this idea of, let's see if I can make this clear. So you have this idea of the circulation on the boundary and then we could come in here and we could look inside and we could ask what's happening with our little wheel all the way inside. So notice that I think it should spin Can you see it spinning? Oh, the speed doesn't change in this case. Just looking at the way this animation is made. So we could somehow, if we looked at all the spinniness inside over the green region, that might tell us something about the circulation that's happening on the boundary. Does the rough connection between the red arrows and the idea of counting the spins inside the region make some sense to people? Are there questions about that?
What does the spinning mean?
Good question. So the spinning is talking something about what's called the flux, sort of a measure of or a way of visualizing the flux. And so think about this like a.
I get it.
Does that make sense?
Yeah, I was just kind of confused what it meant, but flux, that makes sense.
Okay. Yeah. So and I assume you've had physics, is that right, Croy?
Yeah, the flux just represents the change, right?
Yeah, and it's like the change, but in a rotational sense.
Yeah.
It's like rotation. It's like a measure of rotation somehow. So the total spins or the flux inside would somehow tell us something, give us something about the circulation on the boundary. Any other questions about this? Very good. All right, so moving on to page 2. So here's Green's theorem, and again, this is the circulation form. And so if we want to calculate the work or the circulation, that would be the line integral along C around the closed path. This is only going to apply to closed paths, the f dot dr. Remember, to find the work or the circulation, what we care about is the tangential form or the tangential component of the field. And so f dot dr is the same as f dot tds. And we could also split that up into its x component, which would be little f, and its y component, which would be little g. So the fact that big F equals FG is important here and helps you understand what the formula means. And so what this formula does is it says that the work or the circulation is equal to the double integral of the partial derivative of G, that's this G here, with respect to X, minus the partial derivative of F with respect to Y. This quantity right here is the two-dimensional curl of a vector field. Okay. Couple notes about this. One is that when you're in the world of line integrals, if you want to evaluate a line integral, then the step 1 is that you have to parameterize. But parameterization is hard. I mean, the examples that you were doing in your homework were probably somewhat challenging, and those were all relatively straightforward. So parameterization is hard. And so this over here, if you want to evaluate work, you have to parameterize. In the other side of Green's theorem, on the other side, no parameterization is needed. That's the good news. The bad news is you have to evaluate a double integral. So let's see if we can interpret it. So the integrand of the double integral is the two-dimensional curl of the vector field. So Green's theorem says that the circulation around the boundary, let's see if we can get our our colors right. So the circulation around the boundary, so that would be what happens when we go around the outside of the region, is equal to the net curl across the region. That would be in here. So let's look at the second manipulate. So imagine that we created a region, right, we cared about. So here's our region, and this would be our path C. And so we could find the circulation around that boundary, like, you know, how much stuff actually took place. But what we're saying is that that's equal to the net curl all the way across the interior of the region. I also want to comment on, help you visualize what's going on. So notice that if you're down here in the lower right-hand corner of the vector field, see how all those vectors are kind of curving this direction, and you can see the wheel is spinning, not quickly, but somewhat quickly here in the clockwise direction. If we moved back more towards the center, you still have that same directions, this kind of like the same direction happening for those vectors, but the wheel's spinning much more slowly because it's not as big a spin. If we were to go up into the upper hand corner, you can see here the spin is going the other direction. So you can imagine that there's places where you've got clockwise curl, counterclockwise curl. You could have big, I think in here, maybe you'll have, see if we can find a spot where there's a little bit faster. Here you got a little bit faster counterclockwise curl. Right in the middle, it's hardly spinning at all. So does that give you a little bit of a picture of what this curl does? I think so. Oh, I've got the fat pen at the moment. Curl would be partial of G, partial of G with respect to X, minus partial of F with respect to Y. And that would be, this would be that spin rate. I think I said flux on the previous page. I may need to add a correction in the video on that note. I'll have to come back on that one. Questions about this animation? Very good. All right, so let's just do an example. So example 1, we want to evaluate the work or the circulation of the line integral around the closed path x to the fourth dx plus xy dy, where C is the triangular curve consisting of the 3 line segments from 0, 0 to 1, 0, from 1, 0 to 0, 1, and from 0, 1 to 1, 0. So let's work through that one on the doc cam. So we're trying to find the total work This is around a closed curve. And so let's begin by sketching the picture. So you can see that that path is going to go around the triangle. So notice in particular, this is a closed path, right? That's what's important. And since it's a closed path, we have the choice or the option to use Green's theorem. Notice that here, f is equal to x to the fourth, comma xy. This is my little f. This is my little g. And so the work, which is the line integral around the path f dot dr, will be equal to the double integral across the interior of the region of the triangle. We'll figure out the triangle in a moment, of the partial of g with respect to x minus the partial of f with respect to y dA. What Green's theorem says. What's the partial of g with respect to x?
Y.
Right, good. And partial of f with respect to y?
0.
Be 0. So this will be equal to the double integral of y, and then we're going to have a dA. So maybe we could integrate this thing.
dx dy.
Yeah, we could go dx dy or dy dx. I'm going to go dy dx.
dy dx. 0 to 1, 0 to 1. I mean 0 to y equals to.
Yeah, we need this line right here, right?
Yep.
So that line would be y equals 1 minus x.
1 minus x. Yeah.
And then 0 to 1. Questions so far?
So we're just integrating depending on the y variable, right?
Well, y and then x. Are you talking about this y?
Oh, yeah. Oh, I don't see the x over there because I saw that also 0 to 1 is the same as y, but it makes sense now.
Oh, yeah. This y here is coming from here, is all that stuff. Cool. All right, let's just integrate it. See what happens. So we're going to get 0 to 1, y squared over 2 from 0 to 1 minus x dx, 1/2 integral 0 to 1, 1 minus x quantity squared dx. So we're just integrating. This is nice stuff. If you put in 0, you're going to get 0 everywhere. If you put in 1, you're going to get a +1 -1. So all that's going to remain out of all that is a 1/3 times a 1/2 or 1/6. What does this 1/6 represent?
Work.
So this would represent the work, exactly. And so, or the work or the circulation. So if you think back to your homework that you just completed, when you were wanting to find work, the first step was always to parameterize. So you'd find your R of t, and then you'd find your R prime of t, and then you do a whole bunch of substitutions, et cetera, et cetera. And so all of your work was around parameterizations. Here, using Green's theorem, if you have a closed path, you have the option of evaluating that work / circulation simply by switching over to a double integral, and no parameterizations are required. Questions?
Seems a lot more useful.
It's really handy. Yeah. And think about the fundamental theorem of line integrals that you worked with yesterday. It was great and easy to work with, but it only worked on which kinds of fields?
Conservative vector fields.
Vector fields.
Yeah, only conservative vector fields, exactly. So it's a wonderful critter, but this doesn't care what kind of field you're working with. It just cares about a closed path. And you're all pretty smart. You can probably also figure that out how you could close a path if need be. Right? So there's some slick tricks to take this powerful tool and make it even more valuable.
Could you repeat why we don't need parameterization here?
We don't need parameterization because, let me go back to the notes. Because when you parameterize, you're parameterizing for a line integral. Here, we're actually just evaluating a double integral and no parameterizations needed.
Makes sense.
Cool, cool. All right. Let's keep going. So we did that. So an interesting application of Green's theorem is that it can be used to find the area enclosed by a curve. In the 1850s and later, this concept was used to develop a tool called a planimeter, with which you could trace the boundary of a region, say on a map, and the device would tell you how much area was enclosed. So we're really used to this concept when we're talking about things like rectangles, right? We know that you might have a base and a height, and you could easily use those boundaries to find the area enclosed. Or if we had a circle with radius r, we know how to find the area of the circle. But what if you were looking at an aerial map and you had a lake, and you wanted to know what's the area of the lake? And so this planimeter, this idea from Green's theorem, lets you literally just walk along the outside. Imagine this, you walk on the beach around the edge of the lake, and at the end of your walk you say, I think the area of the lake is such and such. It's pretty cool. And so you can derive the formula yourself, but the formula comes from applying Green's theorem to two fields. This one, big F equals 0, x. And this other one, 0, x and y, 0. And so their formula, or their difference, gives the following formula, where the area is given by 1/2 the line integral around x dy, or line integral around c of x dy minus y dx. I saw a video a couple years ago where you could build one of these planimeters using Legos. I haven't done it yet, but I've been wanting somebody to get the idea, and I'm like, man, I would love to have one of these things. That'd be pretty cool. So sort of on my bucket list of projects for students to work on. Can we do one example of with this last formula?
Sure.
Cool. So I'd like to use Green's theorem to derive the area of an ellipse. And you'll probably will recall that we've found the area of lots of regions, circles, blah, 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 using single integrals and then later using double integrals. And here we're going to do it instead of, we're going to use it using Green's theorem, using a line integral. So here's the idea.
Should it be on the doc cam?
It should. Thank you. That better?
Yep.
So the area of the ellipse in general would be the double integral across the ellipse of 1 dA. Why is it 1?
Per unit area?
Yeah, because we're looking for area, and so double integral with an integrand of 1 would give you area. Good call. And so by Green's theorem, this would be equal to 1/2 the line integral around the ellipse instead of across the body of it of x dy minus y dx. So in the last example, we went from a line integral to a double integral. Here I'm going to go from a double integral to a line integral. I'm kind of going in reverse. So since I'm trying to evaluate a line integral, what's step 1?
Parametrize?
Parametrize. So we need to parametrize the ellipse. So we have r of t equals a cosine t, b sine t. We're going to need to find r prime of t. So that would be minus a sine t, comma b cosine t. Notice that this tells us that dx is equal to what?
Negative a sine t.
Negative a sine t dt.
Yeah, dt.
And then dy would equal b cosine t dt. So at this stage, we can just plug and play and see what happens. So here's our formula. So we're going to get 1/2. Oh, and we also need to say where our parameters live. Where does t live between?
It's not 0 to 2 pi, is it?
It sure is, because it's around a loop. So we're going to go 0 to 2 pi. And then we have x, which is a cosine t, times dy, which is b cosine t dt, minus y, which is b sine t, times dx, which is negative a sine t. All this stuff is integrated with respect to t. You see what's going on here? You have a AB here, a BA there, and you have cosine squared plus sine squared. So all this stuff would be the integral of what?
AB.
AB dt. No t's involved, so this would just simply be 1/2 AB times 2 pi, or
AB pi.
AB pi or pi AB, whatever you want to call it. Super slick, fast derivation of the area of an ellipse.
10:30, Dusty.
And it's 10:30. So there's your introduction to Green's theorem. A couple of concluding notes. Note one, tomorrow when we pick this up, we will talk about the divergence flux version. Yeah, the divergence flux version of Green's theorem. Here we were talking about the work circulation version. And then the second note is that I have a separate video that's already posted that does a proof of Green's theorem. So for those of you that are wondering where it comes from, I'd encourage you to watch that video. And I think it's only about 10 minutes long, which would explain where the video comes from. So thanks everyone. I will see you all tomorrow. And tomorrow we'll be back to our normal 50-minute classes. Take care everyone. Have a wonderful day.